Welcome to this explainer where we're going to unpack the hidden physical chemistry of everyday materials. We're looking at the delicate forces that literally govern the world around us. Have you ever wondered why milk is white, how fog just kind of hangs in the air, or why certain medicines can be perfectly delivered straight to your specific cells? Well, the answer lies in a fascinating, honestly almost magical state of matter. It exists right in the sweet spot between the microscopic molecules we can't see and the bulk objects we interact with every single day.
Okay, so here's our roadmap for today. We've got 1. Welcome to the mesoworld, 2. Anatomy of a colloid, 3. Diagnosing the dispersed phase, 4. The stability paradox, 5. Breaking and shielding, and 6. The universal interfacial state. Let's jump right into this microscopic drama happening right under our noses.
All right, Section 1, welcome to the mesoworld. Let's figure out exactly where this invisible realm sits.
So, positioned perfectly in this transitional realm, we find colloidal dispersions. If you look on the far left of the scale here, we have true solutions, right? Like salt water. Those particles are less than 1 nanometer, super tiny. Then on the far right, we have suspensions, like shaking up sand in water, where the particles are larger than 1,000 nanometers. Colloids exist precisely in the middle, between 1 and 1,000 nanometers. They occupy this unique mesoworld, where the particles are just large enough to have distinct surface boundaries, but still small enough to resist just sinking to the bottom of the beaker.
When you compare these features, you immediately see why colloids are so tricky to study. They are absolutely masters of disguise. A colloid will look completely homogeneous to the naked eye, just like a true solution, but physically it's actually heterogeneous. And unlike a suspension that settles out under gravity, a colloid just hangs there. It doesn't settle because it's what we call kinetically stable. You can even pass it right through standard filter paper. It's completely distinct from both solutions and suspensions in almost every behavioral category.
Moving right along to Section 2, Anatomy of a colloid. Let's build our understanding of what actually makes up this unique state.
The absolute crucial point to take away here is that a colloid is not a specific type of chemical substance. You are not going to find colloid listed on the periodic table. Instead, it's a specific two-phase geometry. It requires a dispersed phase, which are the discrete individual particles or droplets, and a dispersion medium, which is the continuous environment that those particles are scattered within.
You can kind of think of the dispersed phase as being analogous to a solute in a standard chemistry mixture, and the dispersion medium as the solvent holding it all together. See how those discrete blue spheres are just floating in that continuous golden background? Because these two phases maintain their own distinct boundaries, they end up creating a massive amount of surface area within the system. And honestly, that boundary area is where all the really interesting physics takes place.
By mixing and matching different solid, liquid, and gas phases, we get an unbelievably diverse array of everyday materials. If you disperse a solid into a solid medium, you get a solid sol, think ruby glass or colored gemstones. Liquid in a liquid medium gives us emulsions, like milk and mayonnaise. Gas in a liquid gives us foams, like whipped cream. Now here's a fun fact. Gas dispersed in another gas always forms a true solution, never a colloid, because the molecules mix perfectly at a sub-nanometer level. But pretty much everything else, cheese, fog, smoke, it's all just different two-phase colloidal geometries.
Section 3, diagnosing the dispersed phase. How do we actually know this is happening? Because these particles are microscopic, living right in that 1 to 1,000 nanometer sweet spot, we face a huge challenge in proving they're even there. You can't just use a magnifying glass, so we use light.
And that brings us to this really beautiful optical phenomenon called the Tyndall effect. When light passes through a true solution, the particles are under 1 nanometer, way too small to interact with visible light, so the beam passes straight through transparently. You don't see a thing. But when light hits a colloid, something magical happens. The particles are between 1 and 1,000 nanometers, which perfectly matches the wavelength of visible light. So they catch the light and radially scatter it in all directions. This illuminates the beam's path straight through the liquid, creating what we call a Tyndall cone. This scattering is undeniable visual proof that a discrete dispersed phase exists in there.
All right, Section 4, the stability paradox. This is the real core drama of our explainer.
Why don't these particles just clump together and sink? Well, the baseline kinetic stability comes from Brownian motion. Imagine our little colloidal particle floating in the medium. It's constantly being subjected to unequal, totally random collisions from the super fast-moving molecules of the dispersion medium itself. This continuous kinetic bombardment shoves the particle around in an erratic, randomized zigzag path. It's like a microscopic mosh pit, And this chaotic dance provides enough kinetic energy to continuously fight off the downward pull of gravity, keeping the particles suspended indefinitely. On top of that, the particles are protected by a complex electrical shield known as the electrical double layer. Around the solid core, ions from the medium attach to form a tightly bound Stern layer. Beyond that is a looser diffuse layer. The boundary between this protective cloud and the rest of the liquid is the slipping plane. And the electrical potential difference across this plane? That's called the zeta potential. It creates a powerful electrostatic repulsion. When two identical particles get close, their negatively charged double layers repel each other, just like opposing magnets. For solvent-hating or lyophobic colloids, this electrical repulsion is the absolute main thing keeping them suspended.
But here's the thing. Despite these awesome defenses, the Brownian motion and the electrical double layer, the continuous kinetic chaos of the microscopic world means that eventually particles are going to slam into each other with intense force. So what dictates whether they safely bounce off or stick together and ruin the entire system?
That question is answered by the DLVO theory, which maps out the ultimate energy landscape of a colloid. You have an attractive force pulling particles together, van der Waals attraction, and you have a repulsive force pushing them apart, electrostatic repulsion. Look at the solid line. That's the net interaction energy. Here is the massive paradox. The particles thermodynamically want to fall into that deep valley on the left, the primary minimum, where they coagulate and stick forever. But to get there, they have to climb over that huge hill, the primary maximum. That hill is the kinetic energy barrier of electrostatic repulsion. So the colloid remains stable simply because it's kinetically trapped. It just doesn't have the energy to jump the fence into coagulation.
Section 5. Braking and shielding. Now that we know the trap, how do we manipulate it? We can introduce specific interventions to essentially erase that protective DLVO barrier we just saw. If we add electrolytes, we flood the system with oppositely charged ions, neutralizing the double layer. If we use persistent dialysis, we strip away the ions that form the double layer in the first place. Or, honestly, we can just boil the whole thing. Adding pure heat increases the kinetic energy of the particles so much that they smash right through the repulsive barrier through sheer brute force.
And when that barrier breaks down, the stable system is totally doomed. Without the double layer pushing them apart, the particles finally succumb to those van der Waals attractive forces. They stick together, forming larger and larger clumps in a process called flocculation, which eventually leads to complete coagulation. Ultimately, those discrete, invisible particles collapse into a massive bulk solid at the bottom of the beaker. The unique colloidal state is officially destroyed.
This leads us to the Hardy-Schulze rule, which brilliantly shows exactly how powerful those electrolyte interventions can be. The rule states that the coagulating effect of an ion increases exponentially with its valency, its electrical charge. To crash a negatively charged colloid, you'd need massive, dumping quantities of a monovalent sodium ion. A divalent barium ion needs moderate quantities. But check out the trivalent aluminum ion on the right. Because flocculating power is proportional to the valency to the power of 6, literally to the power of 6, you only need tiny trace quantities of aluminum to completely crash the entire colloidal system.
On a flip side, we don't always want to destroy colloids, right? Often we want to save them. We can shield unstable particles by wrapping them in long solvent-loving molecules. It creates this physical bumper car effect. The effectiveness of this shield is measured by the gold number. Now, counterintuitively, a lower gold number indicates a higher protective power, kind of like golf. Gelatin, for instance, has an exceptionally low gold number, making it a phenomenally powerful protective shield, whereas starch has a high gold number and gives very poor shielding.
Section 6. The universal interfacial state. Let's bring it all home.
Why does this delicate dance of braking and shielding matter to us? Because this physical chemistry is everywhere. In environmental engineering, we use the Hardy-Schulze rule by adding trace amounts of aluminum to city water supplies to aggressively coagulate and filter out mud and pathogens. In food science, we use protective colloids to stabilize emulsions so the fat in your milk doesn't separate. In pharmacology, we engineer microscopic liposomes to wrap active drugs for highly targeted release in your body. And in nanotechnology, synthesizing quantum dots relies on the exact, precise control of that electrical double layer. I really hope this explainer has shown you that what might look like a simple glass of milk or a beam of light through the fog is actually a complex, invisible tug of war. Understanding the delicate stability of the colloidal state reveals the profound, microscopic physics holding our everyday world together. If manipulating these tiny electrical layers lets us purify water and target cancer cells today, just imagine what we're going to be able to engineer tomorrow.
Keep questioning what you see around you, and I will catch you in the next explainer.